Welcome back to the AI Black Box podcast. Today, we're diving deep into the world of convolutional neural networks,
Okay.
specifically a model called ConvNet that's shaking up our understanding of AI
Oh, wow.
and challenging some long-held assumptions.
I'm intrigued already.
Yeah, ConvNet is turning heads because it's going toe-to-toe with, and in some cases even beating the rock stars of the AI world.
Who are we talking about here?
Vision transformers.
Okay. Yeah, those are impressive.
For a while, it seemed like transformers were destined to completely replace convNets, especially in computer vision.
Well, there's a good reason for that.
Hmm.
In the 2010s,
Mhm.
ConvNets were the undisputed champions of image processing.
Right.
Their strength lies in a technique called sliding window, where the network analyzes small sections of an image at a time,
Okay.
building up an understanding of the whole picture piece by piece.
Like a puzzle.
Yeah, exactly like a puzzle. This makes them particularly good at tasks like object detection.
So if you're trying to find, say, a cat in a photo, a convNet can pinpoint its exact location,
Right.
even if it's partially hidden or surrounded by other objects.
That's powerful.
But then around 2020, vision transformers burst onto the scene.
They really did. They changed the game.
Yeah.
And they excelled at capturing the overall context of an image.
Okay.
The big picture, as some might say.
Mm-hmm.
This made them incredibly good at image classification,
Okay.
determining what an image is about.
Mm-hmm.
However, they weren't as naturally suited to those tasks requiring detailed localized analysis,
I see.
like the object detection that ConvNets were built for.
So it's almost like having two specialists.
Hmm.
One who could tell you the overall style of a painting,
Okay.
but couldn't identify the individual brushstrokes,
I see.
and another who could meticulously analyze every detail,
Mm-hmm.
but struggle to understand the artist's overall intent.
That's a great analogy. And this led to a period where researchers tried to combine the best of both worlds, creating hybrid models that integrated elements of both ConvNets and vision transformers.
Interesting. So like a hybrid car.
Yeah, exactly.
Okay.
The funny thing is, in trying to move away from convolutions,
Okay.
these hybrids actually ended up highlighting the value of convolutional principles.
It's almost like they rediscovered the power of the original approach.
Exactly. Which brings us to ConvNet.
ConvNet, okay.
This model was born out of a research project by Facebook AI, where the team set out to essentially modernize a standard ConvNet model called ResNet.
ResNet.
And they did this by borrowing inspiration from the very architectures that seem to be eclipsing ConvNet's the transformers.
So they're taking inspiration from their competitor.
Yeah, it's like learning from your rival to improve your own game.
It was a systematic approach.
It really was.
Okay.
They took ResNet and step by step, they
Okay.
incorporated elements inspired by transformer design and training techniques.
Interesting.
And the results were pretty remarkable.
Let's break down these steps,
Okay.
because there are some serious aha moments here.
All right, I'm ready.
One of the first things they did was simply change the way the ResNet was trained,
Oh, interesting.
just by using techniques commonly associated with vision transformers.
Okay.
They saw a significant jump in performance.
It was an early indication that the perceived superiority of transformers might be partly due to the way they were trained, rather than being solely a function of their architecture.
Interesting.
This highlighted the critical role training methodologies play in shaping a model's performance.
It's like realizing you've been using the wrong baking techniques your whole life.
Yeah.
The ingredients might be top-notch,
Uh-huh.
but with the right techniques,
Yeah.
suddenly you're creating culinary masterpieces.
I like that analogy.
So beyond the training,
Mm-hmm.
what were some of those key architectural tweaks that gave the ResNet a makeover?
Well, one major change was inspired by Swin transformers,
Okay.
a successful hybrid model.
All right.
They adjusted something called the stage-compute ratio, which essentially controls how much computational power is dedicated to different parts of the network.
So it's like allocating resources within a team.
Exactly.
If one stage needs to do the heavy lifting, you give it more manpower.
Precisely.
Hmm.
And they also borrowed the concept of a patchify stem cell from Swin transformers.
Pagify stem cell.
Remember how ConvNets use that sliding window approach?
Yeah.
Well, the patchify stem essentially divides the input image into smaller patches before processing,
Okay.
which makes the initial stages more efficient.
So they're streamlining the process from the very beginning.
Exactly.
What else did they borrow from the transformer world?
They incorporated a technique called depth-wise convolution,
Okay.
which focuses on processing information on a per-channel basis.
Hmm.
And this is where we see a fascinating parallel between ConvNets and transformers,
Okay.
because attention mechanisms in transformers also operate on individual channels.
So instead of looking at the whole image at once, they're breaking it down into its fundamental components and analyzing each separately
Yeah.
before piecing it all back together.
Uh,
It's like analyzing a piece of music by focusing on individual instruments before appreciating the symphony as a whole.
Precisely. And this shared approach to information processing suggests that these seemingly distinct architectures might have more common ground than we initially thought.
It's like discovering that two artists from completely different schools are actually using similar techniques, just expressing them in unique ways.
Yeah, a great point.
Another intriguing element they incorporated was the inverted bottleneck.
Oh, yes, that's a key one.
Okay, tell me more.
This involves expanding the network's capacity in the middle layers,
Okay.
allowing it to process more information before narrowing down again.
It's like having a wide entrance to a building with a
Ah.
bottleneck, and then a spacious room where everyone can mingle before exiting through another bottleneck.
A perfect way to visualize it. This approach actually has roots in earlier ConvNet designs,
Sumptuous.
notably MobileNet v2.
MobileNet v2.
It's a reminder that innovation in AI isn't always about inventing something completely new. It's often about refining and reimagining existing ideas.
It's a beautiful example of how ideas can evolve and circle back, building upon previous work to create something even better.
Exactly. And speaking of revisiting ideas, I'm curious about kernel size.
Kernel size, okay.
That was a big difference between traditional convets and transformers, right?
Yeah, that was a major distinction.
Transformers, with their global receptive field, could analyze an entire image at once.
Okay.
Traditional convets, however, relied on smaller kernels, typically 3x3,
Yep.
which limited their view to local neighborhoods. With ConvNet, they decided to experiment with larger kernels.
I'm intrigued.
Okay, so,
What did they find?
well, they found that a 7x7 kernel size was the sweet spot.
7x7.
Okay. It provided a balance between capturing broader context like a transformer
Okay.
and maintaining computational efficiency.
So they found a way to expand the ConvNet's field of view without sacrificing speed.
Precisely. That's a key insight.
That's clever.
It was a key step in bridging the gap between the local focus of ConvNets and the global perspective of transformers.
Okay.
But they didn't stop there. They also made a series of smaller but still impactful micro-level adjustments inspired by transformer design.
So like fine-tuning.
Yeah, exactly.
What kind of adjustments are we talking about?
For example, they swapped out the WriteLU activation function,
Okay.
which was commonly used in ConvNets for GELU, which is known for its smoother response.
GELU.
They also reduced the number of activation and normalization layers, mimicking the streamlined design of transformer blocks.
So it's like they were fine-tuning the engine, making subtle adjustment to improve overall performance.
Exactly.
It seems like every design choice was carefully considered.
It was a very systematic and meticulous process.
And one of the most intriguing decisions they made was to switch from batch normalization to layer normalization.
That was a bold move.
Batch normalization had been the standard in convets, but transformers typically use layer normalization, which normalizes data across features instead of across batches.
Exactly.
That must have been a bold move going against the established norm.
It was. But surprisingly, ConvNet actually performed better with layer normalization.
Really?
Yeah, which challenged conventional wisdom in the field.
It's one of those moments where you realize the rules are constantly being rewritten in AI.
It really is.
It highlights the importance of challenging assumptions and experimenting with new approaches.
I completely agree.
And speaking of new approaches, they've meticulously redesigned this ResNet, taking cues from transformers at every step.
They really have.
Now, the big question is, did it pay off?
That's the million-dollar question, isn't it?
How did ConvNet actually perform?
That's where things get really exciting.
All right, so they built this Frankenstein's monster of a ConvNet,
Frankenstein's monster. Yeah, I like that.
borrowing the best bits from transformers and challenging the status quo. Now, the question on everyone's mind is, did it work?
Well, they put ConvNet through its paces on ImageNet,
Okay, ImageNet.
a massive data set commonly used to benchmark image classification models.
Right.
And the results were pretty impressive.
Okay, I'm on the edge of my seat here.
ConvNet didn't just hold its own against the reigning champion.
Who was that?
the Swin transformer.
Swin transformer.
It actually outperformed it in many cases.
Wait, so this modernized ConvNet beat the transformer at its own game?
It did. In some instances, ConvNet achieved accuracy gains of up to 0.6% over Swin transformer.
Wow.
While also processing images faster.
So it wasn't just about raw accuracy, it's about achieving that accuracy with speed and efficiency.
Exactly. That's a double win.
That's amazing.
The researchers didn't stop there. They scaled up the models and tested them on an even larger data set, ImageNet 22K.
ImageNet 22K.
Which contains significantly more images and categories.
So bigger data, bigger
Oh,
challenges. Did ConvNet maintain its edge?
It did. It consistently performed on par with or even exceeded the performance of Swin transformers, even in this more demanding setting.
Wow, so it can handle the big leagues.
It can. It challenges the assumption that transformers are inherently better at handling large-scale data sets.
It's like proving that a classic car with the right upgrades can still outrun the newest sports cars on the track.
Exactly. And to really push the limits, they created an even larger version of ConvNet called ConvNet XL.
ConvNet XL.
Which achieved a remarkable 87.8% accuracy on ImageNet.
87.8. That's impressive.
Yes.
So they're not just tweaking an existing model. They're building a whole family of ConvNets. Each more powerful than the last.
Exactly. This demonstrates that ConvNet is not only a powerful architecture, but also a scalable one, capable of handling increasingly complex datasets and tasks.
So it has room to grow.
It does. But, of course, we can't stop at image classification. ConvNets have historically been used for a wide range of computer vision tasks, like object detection and semantic segmentation.
Okay, so it's not just about recognizing what's in an image.
No.
It's about understanding the relationships between objects and even labeling every single pixel in the image.
Right, that's where things get really complex.
Did they test ConvNet on these more intricate challenges?
They did. For object detection, they used the ConvCO dataset.
Okay, ConvCO data.
A standard benchmark for this task.
Right.
They implemented ConvNet within frameworks like mask-RCNN and Cascade-mask-RCNN, comparing it to both Swin transformer and traditional ConvNets like ResNex.
So it's a head-to-head competition across different architectures.
Exactly.
What were the results?
Once again, ConvNet consistently performed on par with or even surpassed Swin transformer.
So it's holding its own.
It is, especially when they use the larger ConvNet models, pre-trained on ImageNet 22K. The performance gains were quite significant.
Can you give us an idea of how significant?
Well, in some cases, ConvNet exceeded Swin transformers' performance by a full 1.0 average precision.
Wow.
Which is a substantial improvement, especially on a challenging task like object detection.
That's a big jump.
It is.
It's not just a marginal improvement. It's a clear demonstration that ConvNet is bringing something new to the table.
Absolutely. And for semantic segmentation, they used the AD20K dataset.
AD20K.
Another benchmark for this task, and a framework called UperNet.
UperNet, okay.
The results were consistent with what they saw in object detection.
Okay.
ConvNet models achieved competitive performance across different model sizes.
So consistent performance.
Yeah, further solidifying its versatility and power.
So ConvNet is proving itself to be a real contender.
It is.
Outperforming transformers in some cases while holding its own in others.
That's right.
But surely there must be some trade-offs, right?
Well, that's a good question.
There's no such thing as a free lunch in AI.
You're right. One potential concern with architectures that rely heavily on depth-wise convolutions is that they can sometimes be slower and require more memory than models using only dense convolutions.
So is all this talk about ConvNet's speed and efficiency just hype?
Not necessarily. As we've seen, ConvNet actually maintains or even surpasses the throughput of Swin transformers in both image classification and tasks that require higher resolution inputs. They've struck a really good balance between performance and efficiency.
So they found a good sweet spot.
They did. And there's another interesting finding related to memory usage during training.
Oh, really?
It turns out that training a ConvNet model can actually require less memory than training a comparable Swin transformer.
Hold on, less memory.
Yeah, less memory.
That's unexpected.
It is.
Yeah.
For example, when training Cascade Mask RCNN.
Cascade Mask RCNN.
Using ConvNet TB as the backbone resulted in a peak memory usage of 17.4 gigabits per GPU.
Okay.
While SwinB required 18.5 GPU.
Oh, so it's more efficient in terms of memory.
It seems to be. So even in terms of memory efficiency during training, ConvNet seems to have an edge.
That's interesting.
It is. It seems like ConvNet is challenging our assumptions on multiple fronts.
Yeah, it's really turning things upside down.
It's not just about accuracy, it's about speed efficiency and even memory usage.
It's like they've found a way to get more out of less.
Exactly.
Yeah.
It's definitely a testament to the careful and thoughtful design of the architecture.
So where does this leave us?
Well,
We've seen ConvNet excel across a variety of tasks, often outperforming transformers, while maintaining or even improving efficiency.
that's right.
But is this just a case of one model outsmarting another?
That's a great question.
Or is there something bigger at play here?
That's a fantastic question, and it leads us to some even more thought-provoking aspects of this research. It's not just about one model outsmarting another. It challenges some fundamental assumptions we've had about the evolution of AI,
Okay,
particularly in computer vision.
I'm listening.
What kind of assumptions?
Oh,
For a while, the narrative was that vision transformers were the inevitable successors to ConvNets.
like they were the next big thing.
Yeah, they were seen as the next step in AI evolution, destined to dominate computer vision tasks.
It felt like a changing of the guard.
Right, the old making way for the new.
Yeah,
ConvNet throws a wrench into that narrative.
it's like a plot twist.
Yeah, it demonstrates that convolutions, those fundamental building blocks of early computer vision models, still have incredible potential.
Really?
Yeah, when thoughtfully modernized and optimized.
So they're not obsolete.
Not at all. It's a great example of how innovation isn't always about completely discarding the old.
Right.
Sometimes it's about revisiting and refining existing approaches with a fresh perspective.
Like breathing new life into them.
Exactly. And ConvNet's design shows that these seemingly distinct architectures, ConvNets and transformers, may actually be more complementary than competitive. By incorporating elements of transformer design, ConvNet highlights the potential for synergy between these approaches.
So they can work together.
It's like realizing that two seemingly different musical genres can actually influence and enrich each other.
Yeah, like jazz and classical.
Exactly.
Well,
This research could encourage a broader reevaluation of the role of convolutions in AI development.
interesting.
Perhaps we were too quick to dismiss them in the race to embrace the newest and shiniest architectures.
It's easy to get caught up in the hype.
It is. It's a valuable reminder that progress in AI often comes from challenging assumptions and exploring seemingly outdated approaches with a fresh lens.
Like looking at them with new eyes.
Exactly. ConvNet's success story really underscores the importance of rigorous experimentation and keeping an open mind.
So don't be afraid to try new things.
Yeah, or old things in new ways.
It's what keeps this field so exciting.
Absolutely.
There's always the potential for new discoveries and the possibility of rewriting the rules.
That's what makes it so dynamic and fascinating.
And this brings us to a final thought-provoking question. If a pure ConvNet, like ConvNet, can match or even beat transformers in tasks where transformers were thought to have an inherent advantage, does this point to something deeper about how visual information is processed?
That's a really interesting question.
Are you suggesting there might be underlying principles of visual processing that we haven't fully grasped yet?
It's possible.
And both ConvNets and transformers might be tapping into these principles in different ways.
That's a fascinating possibility worth exploring. Perhaps there's a more unified theory of visual processing waiting to be uncovered, one that transcends the specific architectures we're currently working with.
It makes you wonder if we're just scratching the surface of understanding how intelligence, both artificial and biological, truly works.
It's a question that should keep researchers and developers busy for years to come.
And that's what we love about deep dives like this.
Me too.
It's not just about understanding the technical details of a specific model. It's about sparking new questions, opening up new avenues of exploration, and pushing the boundaries of what we know about AI and the nature of intelligence itself.
Well said. So we'll leave you with a challenge.
Okay.
Delve deeper into this research.
All right.
Explore the connections between ConvNets and vision transformers, and see if you can uncover those fundamental principles that might be driving these incredible advances in AI.
So go out there and explore.
Exactly.
Who knows? You might be the one to crack the code and unlock the next breakthrough in AI vision. That's all the time we have for today's deep dive. Till next time, keep those brains buzzing and those curiosity engines running.